field of artificial intelligence has been moving extremely quickly in the last few years. Do you know how AI will affect your life in the future? I have some ideas. I'm Jeff Dean. I'm a Google Senior Fellow at Google. That means a couple of things. First, means I'm kind of old. Second, it means that I get to spend my time working on problems that I think are the most important for the company. I'm working on artificial intelligence. I lead the Google Brain team, our artificial intelligence research team based in Mountain View, California. Our team does long-term research on how to make machines intelligent. And we then work with product teams at Google in order to make machine products that are intelligent. We want to use intelligence to augment the abilities of people, to enable us to accomplish more, to eliminate tedious, repetitive tasks, and to allow us to spend more time on our creative endeavors. AI is going to be more impactful than the invention of the personal computer and the spread of mobile phones into your pocket. So the idea of artificial intelligence is not new. It's been around since the very earliest days of computing. It's a grand project to build machines that are intelligent. And there's many ways of pursuing this. It's captivated computer scientists ever since. The most promising approach, though, is the area of machine learning. Rather than trying to embody machines with everything they need to know up front, rather, we want to enable them to learn how to learn, so that they can learn from their observations of the world and to make inferences based on those observations. The field of deep learning is a particular kind of machine learning that I'll be talking about. And it's been shown in the last 4 or 5 years to be remarkably effective for a wide variety of problems, although it's actually much older. Before we start, though, how do we learn? Why, we learn from examples of things and from repeated practice. And repeated practice and examples are really key to machine learning as well. So in machine learning, we're going to expose a system to examples of the behavior we want it to have. And those examples are going to teach it. It's going to learn from those examples how to do something. So in this very simple diagram, I have a model where we're going to try to teach a computer to tell whether a photograph contains a cat or a dog. And we're going to have examples where we know the right answer. So we have some that we say, that's a cat, that's a dog, that's a dog, that's a cat. And we're going to essentially show the computer an example and say, what do you think? And they're going to say, well, I think that's a dog. And there you go. If you get the right answer, you're done, right? Just like doing your homework problems, if you get it right, you don't have to do more. But if you get it wrong, we're going to make little adjustments to how we believe about what we believe about the world and what we believe about this example to make it more likely that the next time we see that example or one like it, we'll get the right answer, not the wrong one. Deep learning in particular has a particular way of doing this that is really important. So it builds these layers of abstraction automatically as part of the learning process, where the lowest level things are things like, does this part of the image contain a little splotch of brown? And then as you go up through the layers, the kinds of things that it learns get more complicated. Things like, is there an ear at this part of the picture? Or something that looks like a couple of eyes? Or maybe some whiskers? And those features emerge automatically as part of the learning process, which is really critical aspect of deep learning. We don't have to tell it how to tell a cat from a dog. It just learns that there's these things called whiskers, and they seem to appear in lots of photos, and they seem to appear more often in ones about cats. And that's really helpful. And those features develop automatically in the learning process. So neural nets can learn much more than just how do you tell a cat from a dog. They can learn to distinguish thousands of different categories of objects, tens of thousands. This is an ostrich or a fire truck or a fireboat, things like that. They can learn from an audio stream to give you a transcript of the words that were said in that audio stream. How cold is it outside? They can take in an English sentence, hello, how are you? And spit out the corresponding French sentence, bonjour, comment allez-vous? Sorry for my French. They can take in the pixels of an image and give you more than just a category about it. They can actually write a sentence, a caption, if you will, about that picture, a blue and yellow train traveling down the train tracks. That shows a pretty high level of understanding of what's going on in that scene. One of the great things about deep learning is that all of those things that I showed you can be expressed using a relatively simple set of algorithms and can be expressed in a common software framework. So we can build a software framework that enables us to express all these different learning problems and then use it over and over for our research and for our products. And so the system we've built is called TensorFlow, and we use it internally for everything that we do in this area. And last year, we decided we would open source it because we wanted people to have the ability to take this software, download it for free, and use it for their learning problems. It's been really great to see different things that people have used it for. So here's one example. There was a Japanese cucumber farmer, and it turns out when you harvest your cucumbers, you have to sort them into all kinds of different categories for sale. Small ones, medium ones, large ones, prickly ones, not prickly ones, straight ones, curved ones. This is pretty complicated and pretty time-consuming at harvest time. So the farmer was able to take a camera and, using a computer vision model that he trained with TensorFlow, actually have the vision model determine what category of cucumber it was looking at, and then rigged it up to some conveyor belts and some little switches that would push the cucumber into the right box. And so this eliminated many days of labor that the farmer and his wife would have to do at harvest time. And that's just one tiny example of something you can do now that would be harder before. So as I said, neural nets are not new. They've actually been around since the 1980s and 1990s, and they showed really promising results on kind of small toy problems then. But they really couldn't show great results on realistic large problems at that time. And the reason is we just lacked enough computational power. The process of making these adjustments to the model on every example and processing every example many times in order to build this model of the world is very computationally intensive. And so we just needed faster computers. Fortunately, we have faster computers now. Computers have been dramatically improving in performance every year for the last 30 to 40 years, and we've reached this point where neural nets are actually practical on real problems. So the computer you have in your phone is now 100 to 1,000 times as powerful as the computers you had on your desktop 20 or 30 years ago. And that makes all the difference. So we now have enough computation. And just to take an example, the field of computer vision. Every year there's a contest where teams compete to see who can give the right categories out of 1,000 different categories when given an image. And in 2011, before people were using neural nets, the winning team got an error rate of 26%, which doesn't sound too good when you think that humans are at 5% on this task. But fast forward just 5 years, and we're now at 3% errors using deep learning and much more computational power. We're actually better than humans on this task. That's a really powerful and transformative thing. Think about this. Computers can now see, and they didn't used to be able to. If you think back to the time in evolutionary biology when animals evolved eyes, that was likely a time of great change, and incredible and amazing things started to happen. And we're now at that point in computing. For example, this is really, really useful if you're trying to build a robot. If you can't see, it's really hard to do stuff. So here we have an example of robots using deep learning to teach themselves hand-eye coordination. So essentially, there's a video camera for each robot. Gets to look over its shoulder, I guess. I don't know. It only has one arm, but over its shoulder. And that model is going to take the pixel inputs from the camera and go directly to 6 torque motor commands for the different joints on the robot. And they're essentially just going to, through trial and error, practice picking things up. And so you see they're just trying things, and they can tell if they succeeded or failed by whether their gripper closed all the way or whether they were actually successful at picking this up. And they're learning like what kinds of grips work well for different shape objects based on the vision that they're developing. And they're pretty good at it. We bought a bunch of variety packs of toys and tools on Amazon. Another area where I think machine learning has incredible opportunities is in the area of healthcare. And I'll give you just one example. So diabetic retinopathy is the fastest growing cause of blindness in the world. There's 400 million people at risk who should really get screened basically every year, but often people don't get the screening they should. So we wanted to tackle this with computer vision. And you get an image like this, and traditionally an ophthalmologist scans this to try to assess how serious the signs are, if there are any. And so we got a large collection of these eye images, and we had human ophthalmologists label them. So if you have a human ophthalmologist, 2 human ophthalmologists score these, they agree with their rating 60% of the time. Slightly more worrisome, though, is if you ask the same ophthalmologist to grade the same image a few hours later, they only agree with themselves 65% of the time. And it's really just a hard problem, right? It's sort of an interpretation of like, how dark are those spots? Should that be a 2 or a 3 in this rating scale? So on. So in work published earlier this week by our group in the Journal of the American Medical Association, we now have a machine learning model that performs on par, perhaps even slightly better than ophthalmologists at this task. And this is really important because it can make ophthalmologists much more efficient. They can actually dedicate their time to the people who deserve the attention and not spend as much time on screening most of the people, most of whom don't have any signs of this. We'll also be more creative. By having tools that understand the art we're trying to create, that'll be really helpful, and I'll show you another example. So Leon Gattis and his colleagues from the University of Tübingen and the Max Planck Institute in Germany last year published this amazing paper where they have an algorithm that can take 2 things, an image, a photograph, and a painting. And what the algorithm does is it renders that photograph in the style of that painter. So here you see that same picture rendered in 3 different styles automatically by those 3 different artists. And that's pretty amazing. And I think there's going to be a real opportunity to create tools for human artists that allow them to really interact with systems like this and to more rapidly get the ideas in their head out into really new and creative kinds of art. Remember how the advance from the 1980s to now was caused by much more computational power. So the same thing is going to be true in the future. We want more computational power so that we can train larger models, so we can learn more. And so deep learning is actually transforming how we design and build computers as well. There's 2 interesting properties that neural nets and learning algorithms we're using have. The first is that reduced precision is OK. It's fine when you're multiplying numbers for a neural net to say, about 1.2 times about 0.6. Sounds about like 0.7. That's good enough. We don't have to spend every last detail of our computational budget preserving all the digits of precision that traditional CPUs and computers are designed to build. And that's really helpful. If you yourself, if you needed to multiply a bunch of things and you were able to be very approximate like that, you could do many more operations. Same thing is happening in neural nets. The other thing is that all the learning systems I showed you and all the algorithms rely on just a handful of specific operations. They don't need the full generality that general-purpose computers have. They want to be able to do things like matrix multiplies, vector operations, things from linear algebra, and that's about it. And so that allows us to build specialized computers that can do these things extremely well and not much else. So here is a system that we've built at Google about in the last 3 years called the Tensor Processing Unit. It's essentially a custom-designed chip that accelerates neural net computations only. But because these kinds of deep learning algorithms are so applicable to many problems, this is great, because we now have something that can speed up those kinds of computations by an order of magnitude compared to traditional CPUs. And that's really, really powerful. It allows us to use more powerful models in our products and get sort of better systems out there. Let me take you on a tour of some queries from the future. One of the things that we've observed is that as systems get more intelligent, users expect more from what they can do. So which of these eye images shows symptoms of diabetic retinopathy? Well, I already showed you. We can actually do that today. Describe this video in Spanish. We can't quite do that. We can describe still images pretty well, but not quite moving videos. But that'll come. Find me documents related to reinforcement learning for robotics. and summarize them in German. That's pretty complicated, but imagine how productive we'll be able to be if we're able to have tools that can do that. Please fetch me a cup of tea from the kitchen. Having robots operate in messy environments like your kitchen is actually pretty complicated, but the very baby steps of things like the hand-eye coordination work I showed you are steps along that path. In closing, AI is going to help us to be healthier, happier, more productive, and more creative. Are you excited to see what the future of AI holds? I really am. Thank you.